At the end of the day, one of the most important concepts we'll explore during this course is chemical bonds. We'll come across bonds of all strengths and compositions that play a host of different roles in fiber and dye chemistry. Today, we are going to go over the three basic types of bonds that hold molecules together: covalent, ionic, and metallic bonds. But before we get there, we need to talk about charges because all bonds boil down to the attractive between two opposite electrical charges. So to review, like charges, negative negative or positive positive, repel each other. To bring two like charges together requires an energy input from the system. For instance, like pairing two electrons in an orbital requires to put energy in. The resulting arrangement is higher in energy than when the charges were separated from each other. On the other hand, opposite charges, negative positive, are attracted to each other. When you bring two opposite charges together, energy is released, or the charges are lower in energy when they are together than where they were apart. Remember, nature is lazy and is always trying to minimize its energy input. So we'll see nature trying to put positive and negative charges together. In atoms, where do these charges come from? Well, from the gain and loss of electrons. And those electrons are the currency of chemical bonds. The simplest definition of a bond is an attractive force between atoms. This force comes from the attraction between positive and negative charges on the atoms, specifically resulting from a loss or gain or sharing, or a loss or gain of a whole or part of an electron. The nature of the bond comes from how these electrons are or aren't shared. Moving around electrons through bonds allows each atom to achieve a valence electron configuration of ns2, np6, to have a full outer valence shell, or to reach that 8-electron state. Covalent bonds is where an electron pair is shared between two atoms. For instance, if we have two hydrogen atoms, each has a 1s1 electron configuration for a total of one valence electron. If hydrogen pools their electrons together to form a bond, each atom now has access to two valence electrons. Is it 8? No. But n equals 1 only has one orbital in it, an s, so both hydrogen atoms now have their outermost end shell filled. How does that work? The 1s orbitals each contain an electron, and the orbitals corresponding to these electrons overlap with each other. The combined orbital encompasses the whole molecule to make a bond. Covalent bonds make the assumption that electrons are evenly shared. Towards the middle of the semester, though, we'll learn that this is not always the case. An uneven electron sharing within covalent bonds is largely how many fibers and dyes are able to stick together. However, there's one special type of covalent bond we'll touch on today, and that's the coordinate covalent bond. The coordinate covalent bond is a bond where one atom donates both electrons in the bond. So the question becomes, what elements make covalent bonds? Both regular covalent and coordinate covalent bonds can be made between two nonmetals or a nonmetal and a metalloid. However, transition metals and nonmetals tend to form coordinate covalent bonds where the nonmetal donates both electrons to the metal. Note that most bonds, with a few exceptions, have both covalent and the next bond, ionic bond character, but we refer usually to one or the other for simplicity. The next type of bond is an ionic bond. Ionic bonds occur when electrons are donated rather than shared. The result is that after the electron is donated, one atom carries a negative charge and the other carries a positive charge. The bond is held together by the attraction, the electrostatic attraction, between the resulting positive and negative charges. If you were to zoom in on the atoms in an ionic compound, you would see the charges line up in a crystalline solid. An example is sodium chloride. Sodium donates its single valence electron to chlorine. Now the sodium ion, which is positively charged, and the chloride, which is negative, are attracted to each other, forming an ionic bond, and the compound we know and love as table salt. Ionic bonds are formed between metals in group 1 and 2 and nonmetals in groups 15 to 17, as well as polyatomic ions. The last type of bond we'll talk about today is a metallic bond. Metallic bond is pretty much a positive ion floating around in a sea of electrons, not unlike how a volleyball lobs around at a volleyball match. In this arrangement, metals give up their valence electrons, which are delocalized or spread around multiple nuclei. This is why pure metals conduct electricity, which is essentially a flow of electrons, so well. Groups 1 to 12 elements in their pure form participate in metallic bonds. For instance, sodium and sodium solid would undergo a metallic bond, but the sodium and NaCl would have an ionic bond. Similarly, when pure metals are mixed together in an alloy, these metals also undergo metallic bonding. An example is brass, which is a mixture of copper and zinc, and while some other common alloys, such as steel, pewter, and bronze.